Hello everyone, my name is Shin. I recently presented a paper on my latest research findings about variance at the Information Processing Society of Japan, and I would like to share its main points with you. In that presentation, I discussed in detail why existing approaches that relied on numerical calculation can generate errors. Variance is important in hardware and software design and analysis. If we handle it accurately, performance and reliability can improve a lot. I have felt this effect through my own experience in developing many products. Existing methods for handling variability suffer from three types of errors, and each of them can be improved through three corresponding steps. 1. Errors in distribution shape. When we use the standard deviation, we implicitly assume that the data follows a normal distribution. As a result, any difference between the actual distribution and the normal approximation becomes an error. To address this, we use kernel density estimation, which provides a more accurate representation of the true distribution following the histogram. 2. Errors caused by numerical calculation. When the data contains multiple sources of variability, the distribution of the computed result is often inaccurate, even when the sample size is large. Instead of performing numerical calculations directly on individual data points, we improve accuracy by calculating the resulting distribution through distribution-based calculation, using the distributions of each variable. 3. Errors in decision-making indicators. Traditional design decisions relied on comparing numerical values, which makes the range of variability ambiguous. We improve this by making probabilistical decisions that consider both the relative positions and the shapes of the distributions. In this talk, I will begin with the second topic, then explain the first topic as the preceding step, and finally cover the third topic as the concluding step. Let me begin with the errors caused by numerical calculation, to clarify the meaning of distribution calculation. Here, data sets E and B represent two independent groups of data, and E plus B represents the set of results obtained by adding them together. Both E and B are independent, and each contains enough samples for their distribution shapes to be considered stable. What I will explain is that the resulting distribution E plus B does not become the correct distribution, even under these ideal conditions. This figure represents the AB space, which is formed by the ranges of data sets I and B. When dividing each distribution and the AB space into M segments, we set the number of samples N to range from 100 to 10,000. Here, M is defined as follows. If we place N data points according to a normal distribution with a width of plus minus to sigma, M is the maximum number of segments such that at least one data point falls within each of the outermost segments. When the operation is addition, each combination of I and B maps to a point whose projection onto the axis, along a slope of -1, gives the value of I plus B. Therefore, the resulting distribution after the operation must lie within this range. Next, we examined how large the region is in which no data points appear near the distribution boundary. This is done by analyzing the number of ways the N samples can be placed into the M segments of the AB space. If none of the combinations fall within the orange region, whose edge length is pame, then for looping the red dashed line here will be no data in boundary region B of the resulting distribution. The probability of this situation occurring. The probability that no data points appear in the missing region is given by the ratio between the number of ways data can be arranged in the entire pyramid shown in the denominator, and the number of ways data can be arranged in the pyramid with the missing region removed, shown in the numerator. When we have between 100 and 10,000 data points, and the distribution fills all the way to its boundaries, the pyramid typically has 6 or 7 layers. For each layer, the factorial of the number of points in that layer represents the number of possible arrangements. The denominator is the product of all these factorials. The number of numerator combinations is the factorial of the sum of combinations at each level minus those reduced by missing regions. Let I be the number of data points in a missing region. The sum obtained by varying I from 1 to MP in this formula represents the number of combinations containing data in the missing region. The term M0 minus I factorial represents the number of arrangements in the remaining region when I points appeared in the missing region. The term to its right represents the number of ways to select I points from the missing region, minus alpha. This gives the number of valid arrangements where I points fall into the missing region. Their product represents the reduction in the number of possible arrangements. Here, alpha represents arrangements that are impossible, such as cases where 2 or more points would fall in the same row or column. For simplicity, we set alpha equals 0, and treat that constraint as an inequality. If the ratio of the numerator to the denominator exceeds 50%, then there is a greater than 50% probability that the missing region contains no data points. To determine the size of MP, I plotted how MP changes when increasing the number of iterations. In this figure, the horizontal axis represents the number of data points n, ranging from 100 to 10,000. The blue line shows the segment width of the original distributions, indicating that at least one data point exists from the boundary up to this range. The orange line represents the distribution after the operation. With a probability of more than 50%, there are no data points from the boundary up to this range. In other words, although the original data contains information all the way to point C, the resulting distribution lacks information in region B. This means that the variability present in the original data is not reflected in the computed result. The region without data remains the same even for subtraction or integration. For product and division, there is a difference between the left and right sides of the distribution, but the average remains the same. In all cases, the value of B gradually decreases as the number of data points n increases. However, the ratio relative to C increases, meaning the probability information is not preserved. Even when the number of data points n is large, the distribution of the calculation results contains error. As methods equivalent to this numerical calculation applies not only to Monte Carlo methods but also to cases where distributions are derived from data containing multiple variances in various measurement results, or where probability calculations are performed. As a solution to address numerical calculation errors, I will now explain distribution calculations. This method determines the range of the resulting distribution directly from the xy space of the original distributions, which possess a minimum and maximum value. Then, by dividing that range into equal segments and calculating the combinations within each segment, we obtain the resulting distribution without any missing regions, and with an accurate distribution shape. For the sum of two distributions, the range is determined by the line with a slope of -1 connecting the upper right and lower left corners to the x-axis. For the ith value, zi, the line along which the sum is constant is also a slope -1 line. The probability of zi is obtained by summing the products of the probabilities along that line, and dividing the total by the segment width to get the distribution value. For the product of two distributions, the range is defined by the product of the closest point to the origin and the farthest point on the xy plane. The line where the product equals zi lies on the red dashed hyperbola. We place lines with a slope of +1 at equal intervals, and for each zi, we sum the probabilities over the region enclosed by the two hyperbolas and the two straight lines. This probability is the area of that region multiplied by the values of the two distributions along it. For details on other types of operations, please refer to the book. Next, to demonstrate how time series simulation can be achieved, I will explain the method using sequential distribution integration as an example. We begin with the initial velocity distribution v0 and the initial position distribution x0. We then divide the xy space into fine grids, assigning each grid a position value, a velocity value, and a probability. These grids are updated step by step over time. After delta t seconds, the position spreads into a diamond-shaped region. After another delta t seconds, the region spreads further, and after n seconds, it evolves into the shape shown here. We then divide the final position range after n seconds into equal segments. For each segment, we sum the probabilities of the grids that fall into it, and divide by the segment width. This gives us the resulting position distribution. This process is what we call distribution integration. Considering everything explained thus far, when examining the overall design and analysis involving multiple sources of variance, I believe that distributions of data equivalent to such calculation results should not be used as Monte Carlo methods or as measurement results for manufactured products or as it was even if big data in order to correctly grasp the variance. Instead, we should identify the individual distributions of A, B, and C, and apply distribution-based computation to each of them. Furthermore, by using the decision indicators that I will explain next, we can make accurate and reliable judgments. I propose following these steps, 1, 2, and 3. The second solution for reducing error is to improve the precision of the distribution shape. The tool generates a kernel distribution from the data and uses it for computation. The orange line is the histogram, and the blue line is the kernel distribution. The kernel distribution is smoothed by averaging the histogram over specified intervals. We randomly generated data for 1,000 people simulating test scores out of 100 points. We calculated a percentile probability for scores of 70 points or higher, as well as the scores corresponding to the top 0, 1% and 1. 0%, and compare these to the true values calculated by counting the data. Here are the results for the normal distribution and the kernel distribution. This shows the error relative to the true values. The normal distribution has an error that is 1 to 2 orders of magnitude larger than the kernel distribution. This table shows the variance in error when using random numbers generated from about 10 different distribution shapes. The values in parentheses indicate the average error. Compared with the kernel distribution, the normal distribution shows errors that are 1 to 2 orders of magnitude larger. The third solution against error is the use of distribution-based decision indices. This tool provides 4 types of indices, and they can be applied to distributions ranging from 1 dimension to 3 dimension, enabling probabilistical judgments tailored to specific purposes. Percentile, this divides the distribution at any chosen threshold and calculates the probability within that region. Comparison, this calculates the probability that one distribution exceeds another, or falls below another. This indicator is especially useful for applications such as component performance evaluation, system reliability design, and many other cases. Proximity, this calculates the probability that two distributions come within a specified distance of each other. Equilibrium, this identifies the balance point or relative influence between two opposing distributions. Next, I will introduce 3 application examples using the comparison, proximity, and equilibrium indicators. A data recorder is a device that stores system or component data at the moment a failure occurs. Here, I will show a distribution-based balancing design that ensures 2 things. 1. The required data is not overwritten, and 2. The memory for specific items does not become excessive. Based on this formula, we designed the system by calculating the probability that the number of days until data retrieval exceeds the number of days until data would be overwritten. From these distributions, if the memory can store data for 10 events, we calculate the distribution of the number of days required for 10 trigger activations. By comparing this with the distribution of days until data retrieval, we can determine the probability that the required data will be overwritten. In this case is 8.4%. This example shows a missile interception simulation performed using distribution-based integral. Here you see the trajectories of the target and the missile. This figure shows the distribution of the points where the missile comes within 20 meters of the target. This one shows the distribution of the closest approach distance, and the probability of coming within 20 meters is 54%. Because both objects follow parabolic motion with variability, achieving a 100% interception rate is impossible. The lower simulation shows the case where, once the missile comes within 500 meters, it switches to autonomous guidance and begins homing in on the target. With this control mechanism, the probability of coming within 20 meters increases to 99%, making interception almost certain. This example simulates the profitability of business activities. The formula on the left derives the consumer demand distribution, based on factors such as income and purchasing motivation. The formula on the right derives the supply distribution, based on factors such as production cost and output volume. Using these 2 distributions, we explored the balance point between supply and demand. Here you can see part of the distribution-based computations used for each side. This figure shows the equilibrium of the 2 distributions. The intersection of the 2 cumulative distributions represents the equilibrium price, and the height at that point corresponds to the sales amount. If 20% of the sales amount is allocated to capital investment for equipment depreciation, the cost decreases, the equilibrium price falls, and as a result, the sales amount increases in the second year. In summary, my analysis shows that, no matter how much we increase the amount of data, numerical calculation always leaves errors at the boundaries of the resulting distribution. Equivalent methods to this numerical calculation typically involves multiple sources of variability as Monte Carlo simulations or various types of measurement data. These indicate that quality cannot be guaranteed unless distributions are generated for each individual variance factor and results are obtained by considering combinations of their parameters. Distribution-based calculation eliminates these missing boundary errors. When combined with kernel distributions and distribution-based decision indices, it significantly improves the accuracy of design and analysis across a wide range of hardware and software applications. That concludes my video. Thank you very much for your attention.